We're recording. Thank you for asking that question, whoever that was.
That was me, Izzy.
All right, thank you, Izzy. All right, so we're going to be talking about the measurements lab. And with the measurements lab, we're going to be talking about how to measure. We're going to be talking about significant figures. We're going to be talking about carrying significant figures through algebra. So I'm just going to put algebra and significant figures. And we're also going to talk about rounding. If we have time, which I don't think we'll have, we'll talk about scientific notation, but that's something that you should probably already be familiar with. Okay, so let's get to measuring. And what I'm going to do here is I'm going to open up our lab about the measuring. So I'm going to do a new share here. I'm going to share my screen with you here. And I have these announcements that are posted. And I'm going to open up the lab for measuring. Now this is section 252, but it's the same for section 253. They are the same lab. Here's the measurements lab. You may also want to look at the announcement because if you want to see the labs in advance, I'm going to put up the old labs eventually, but I'm modifying them so it'll just give you an idea of what to do. It won't be exactly what we do. So if we take a look at this, you can see that I'm starting off with what you're supposed to write up and what you're supposed to do for this particular assignment. You want to write it up in your lab notebook, have a title, intro, safety, etc. You want to submit the following photos: your paper ruler on a scale so that the numbers on the scale are visible, the meniscus of the water in your graduated cylinder, and the length of the card shown the store ruler next to the card so the numbers on the ruler are visible. Those will make more sense when we look at the procedure. You also want to answer the questions at the end of the lab and submit answers. In this particular case, the questions at the end of the lab, which I'm going to jump to now, here are the questions. Number one, determine the area of the card using the measurements from the store-bought ruler and using the measurements from the self-made ruler. That's a calculation. So you want to do that calculation, but now I'm going to scroll back up. You'll notice there's a calculation section in your lab write-up that you're going to put in your lab notebook. And this says based on the assignment. So you can put that calculation in the calculation section. And for the assignment below, you can say, refer to the first calculation in the calculation section. And that's perfectly fine. All right. So let's move along here. This describes how to measure. And I'm not going to read this to you. I'm going to show you how to measure. So I'm going to do another share here, and I'm sharing my desktop. And when I say desktop, I don't mean what is on my computer screen. I mean what is on my desk. So can you see my hand? Excellent. So this is a balance. This is the one where I sent you a link to it that you should buy a balance. I like it because it's very small. It was inexpensive, and it's pretty easy to open, and it's pretty easy to use. So to turn it on, I just hit this on button, and it's on. It takes a little while for it to settle. It reads down to the 100th. And right here, that little symbol there is a G, which is a gram. Maybe if I zoom in a little bit, you can see that better. And let me try to focus. Okay, now I don't have any sort of studio lighting, so the lighting I have is not the best. And that's why the number looks kind of weird. Let me see if I turn this light off, if it gets a little better. Nah, not really. Okay. So if I were to put an object on here, this says 6.76 grams. Now, when you're weighing something on a balance like this, which is a digital balance because we have a digital readout, you write all the numbers down. but that 6 at the end is close to what it should be. It may actually be 6.75. It may be 6.77. In fact, if I had a different balance and I put the same ruler on it, it might very well read 6.78 grams. So the idea here is that we're sure about the first 6, we're sure about the 7. The last 6 is a good idea of what that number should be, but it may not be perfect, okay? So even though it's not perfect, it does have information. We know it's not a 1, we know it's not a 2. We're fairly certain that it's above 5. So that is useful information. So on a digital scale, the last number is a really good guess as to what the number should be. You write all of the numbers down. Now that is as compared to an analog scale. An analog scale is basically a scale that does not have a digital readout. So this is an analog scale. Now, I'm certain all of you know how to read a watch, even though it's not digital. So here we go, an analog scale. I'm going to show you another analog scale in just a moment here. I'm going to turn off my balance. And here it is. This is an analog scale. There's no digital readout. And now I'm going to show you another analog scale. This is a graduated cylinder. And when you use a graduated cylinder, I suggest you don't use it laying down on the tabletop because all the liquid will flow out of it. I'm just doing this so you can see the numbers. Fair enough? That's the question. Fair enough? All right. So how do you use an analog scale when you're measuring things? Well, the best way for me to show you is to use an analog scale and show you how to do that. Now, I'm going to put this on a piece of paper because part of your procedure, even though we haven't looked at it, part of your procedure is to take your ruler and make a paper ruler. So this is how you do it. Trace it. I'm going to put a little mark here at 0, at 1, at 2, at 15, and I'm going to put marks all the way up at all of the numbers. And then I'll bring those marks down like this. This is going to be 0. This will be 2. This will end up being 15. And you'll end up making a ruler that looks like this. So this is my ruler that I made from my paper ruler. And if you look at this, you can see that the numbers match up pretty well. Okay? So you need to make a paper ruler. Now, if we look at the paper ruler, you can see that I wrote centimeters here because the idea here is that this is 0 centimeters, this is 2 centimeters, this is 4, and so forth and so on. I have an index card here, and you need to measure the length and width of an index card in centimeters. We use metric units in science, we don't use English units. Now, if you don't have an index card, you don't need to run out and buy one. You can use a business card. Just make sure that the business card doesn't have rounded edges. You want to kind of avoid that. Okay, so if we were to measure the length of this index card, I like to line up the 0 with one edge and then read the other edge, and I can make a direct measurement as to how long this is. I could start at 1 and measure to the other end, and you can see that this is 13 something, but whatever value I get here, I have to subtract 1 from it because I'm starting at 1. So naturally, we like to start at 0 and read to the other end. Okay, so I'm shoving this over, and you're going to have to trust me that I'm putting the 0 at the edge of the card, and we want to focus on this side here. And I'm going to move this over just a little bit so that we can zoom in just a little. And when we zoom in, I think we can all see that the value is larger than 12, but smaller than 13. So what do we write down? And the answer is really simple. First of all, we find out Can you guys hear that message? Oh, you can't. All right. So remember, you can donate at the blood bank. All righty now. So this is 12 centimeters, this is 13, and this is 14. So regardless of what analog device you're using, to find out how far to measure, you look at the smallest increment or the smallest division or the smallest space between two adjacent lines. So if this is 10 and this is 11, that's a 1 centimeter difference. 11 to 12, that's a 1 centimeter difference. Once you identify that amount, you measure to 1/10 of that amount. So because this is 1 centimeter, and hang on a second, folks, I'm going to pause this. Pause. And we're back. So as I was saying, what you do is you find the smallest increment and you measure to 1/10 of that amount. In this case, since the smallest increment is 1 centimeter, you measure to 1/10 times 1, which is 1/10 of a centimeter. Okay, so if the smallest increment, if you take a look here, this is 12 centimeters and this is 13 centimeters, but it's divided into 10 equal spaces. So the smallest amount here is 1/10 of a centimeter. So we measure to 1/10 of that. So what's 1/10 of 1/10 of a centimeter? It's 1/100th of a centimeter. So this guy, we measure to 100th of a centimeter. We record to 100th of a centimeter. They are the same thing. And for this guy, we measure to 1/10 of a centimeter. So let's go back to this guy and let's write down what we would write down for this value here. So I think it's more than halfway past 12. So I don't want to write 12.5. That would be halfway. 12.6 would be a little bit more than halfway. I would write down 12.7 centimeters. And that would be appropriate. We don't want any numbers after the 7. Some of you might look at this and you might decide that you think it's really 12.6 centimeters. And if you did that, I'd say, fine, I'm with you. That's great. Some of you might write 12.8. I'd kind of shake my head at that and say, I don't quite think so. Some of you may look at this and say, you know what? That looks like it's exactly 3/4 of the way. So I'm going to call it 12.75. That's inappropriate. You cannot know that it's 12.75. And the reason for that is if you say it's 12.75, that means that there's no way in the world it's 12.70. And that's just not appropriate with that particular scale. So I'm going to zoom out a bit. And we're going to write this down very quickly. For the digital, you write down all the numbers. For the analog, you determine the smallest division, which is also the smallest increment, and you measure to 1/10 of that amount. Okay, so that being said, just for practice, I'm going to put my index card here again, and we're going to take a look at the width. I'm going to line up the 0 with one edge of the card, and we need to measure the width of this. Okay, can everyone see the edge of the card underneath the ruler? This is the edge right here. I'm going to draw a line next to it. That's the edge. So what I want you to do is I want you to write down what you think the value is. And when you have a value written down, give me a thumbs up or a check mark or something like that, so I know that you've done it. Okay, now we see why there's such a long line here in the middle, is so that we know where 7.5 is. So we don't need to start here at 7. We can start here at 7.5 and see that it is almost 7.7, but not quite. So what should we write down? I'm going to zoom out a little bit in a moment, but it's really close to 7.7. So I'm going to call it 7.69. Now, I'm going to move the ruler over just a little bit. I shouldn't do this because that's not appropriate based on the 0, but I'm going to move the ruler over just a little bit and zoom back in. Now, what if this is what we saw? We think that the edge of the line is right on the 7.7. What should we write? So what I'm going to do here is I'm going to move this all down just a little bit. Too far, apparently. So we think it's right on the 7.7. What should we write? Well, if we write 7.7 and that's it, that means that this 7 here is wishy-washy. It could be an 8, it could be a 6. How do we convey to people that we think it's right on the 7.7? And the answer is you put a 0 here. So in this particular case, the smallest division is 1/10 of a centimeter. So we need to be able to measure to 1/100th of a centimeter. And that number here could be 0, 1, 2, 3, all the way up to 9. It's going to be 0 if it matches on the line. Okay, so I hope you did well with that measurement and you got something close to 7.69. If you had 7.68, that's absolutely fine. If you had 7.7, that would not be okay. So, are we good to go? Okay, then we're going to move on. Now, here's the graduated cylinder. And you'll notice that when I arrange this the proper way, there we go, you can see the ml at the top. That means that every unit here is 1 milliliter. And if I zoom in on this just a little bit, can you see the 100 and the 90? So there are 10 spaces between the 90 and the 100. Each space is 1 milliliter. So what should we be able to measure to? And what I'm going to do is I'm going to shove this over just a little bit. Well, if the smallest amount is 1 milliliter, we should be able to measure to the 10th of a milliliter. Okay? Now, when we're measuring liquids, and I'm going to need to zoom out a bit here, liquids act kind of funny in graduated cylinders. So here's my graduated cylinder. I'm going to call this 90 and I'm going to call this 80. And here I'm going to divide it into 10 equal spaces. And this is what a liquid will look like inside of a graduated cylinder. It looks like it has a bit of a concave shape to it, where the middle of the water is lower than the outside of the water. The reason for that is this middle, which is called the meniscus. The middle of the water is lower because the sides of the water that are close to the glass actually try to climb up the glass. The sides of the water, they're attracted to the glass of the water, so they climb up it. So you measure to the meniscus. And if we look at this guy right here, and I draw a little line going across from the meniscus to the side here, based on my line, we would write down the value of 83 point, and we have to decide, is that halfway past 83? So we'd call it 83.5. I'd say it is not. And so I'd call it 83.3 milliliters. Now, if you want to call it 83.4 milliliters, I'm not going to argue with you. If you want to call it 83.2, I'm not going to argue with you because they're all pretty close to one another. So are we okay with the value we would read here based on my drawing and the line I've drawn across from the meniscus towards the edge? We okay with that? Okay, now, life is not so simple. Oh, we have a raised hand. Izzy, go ahead.
I have a question because now I think I'm a little bit confused. So, you said that the level of measurement is based on the tick marks, right? That
Yes,
are on the analog. I'm sorry, what you called it, analog
analog device. And so
device.
here the tick
Okay.
marks are the milliliters.
So, 83.3 is what you know to accuracy, but you can add or right. I don't know if it's accuracy, if that's the right word to use, but 83.3 is can't you add an additional like estimated number after the point 0.3?
No, the 0.3 is the estimate. Let me zoom in on it a bit.
Oh, okay.
So what I'm going to do here, Izzy, is I'm going to point to that. That's 81. Oh, and I need to zoom out a little bit because you can't see what I'm writing. So this tick mark here at the bottom is 81. This is 82. This one's 83. The line I've drawn across to the edge is an imaginary thing. We can't actually see it. Does that help at all?
Right. So I do see the 83 tick mark. I guess I was just wondering. Oh. Never
And this
mind.
one is
Never
84.
mind. Never mind. I was thinking, yeah, I was looking at it wrong.
Yeah,
Sorry.
I think you were thinking that the line I've drawn
I guess
here
because
is
it's two
actually on the
threes.
cylinder, but it's not.
Because it's two threes, I got confused. I was like,
Okay,
never mind.
so we're good to go, right?
Yeah, I'm good.
Okay, that's fantastic. As long as we've settled that. So it turns out that reading a meniscus is not this easy because you see, I have the water climbing up the sides, right? And you can see that it's climbing up the sides, but the front of the graduated cylinder is a side. So the water is going to climb up the front also. So it starts to get confusing. Let's look at a real meniscus. Okay, so I'm going to change my share screen. And I'm going to type in meniscus, and I'm not going to make the mistake of typing in only meniscus, because if I do that, we're going to see a bunch of knees and the meniscus on the knee. So I'm going to put graduated cylinder because that helps a whole lot. And here we're going to see some images of graduated cylinders and the meniscus. So I'm going to choose this guy right here. And what I want you to see here is just how tough it is to see the meniscus. Do you see that? So what I want you to do now is take a look at this amount. And if I move the image a bit, can you see at the top it says milliliters? So we're measuring in milliliters. I want you to take a moment here and write down the measurement you would use for what we see here. When you're done, give me a little thumbs up or a yes, meaning that you're done. Okay, we've got enough responses. Now this, you can see my cursor here. So this right here is 80. This is 81. This is 82. And it's tough to see, but this is where 83 is. I'm going to leave my cursor at 83. And we can see that the meniscus actually drops below 83. So the meniscus starts where the water is clear and all of a sudden it doesn't look clear anymore. And what I'm going to do is I'm going to drop my arrow to the bottom of the meniscus, and there is my cursor at the bottom of the meniscus. So to me, it looks like it's more than halfway past 82. So I'm going to call it 82.7. And that's my measurement. If you said 82.6, I think that's fine. 82.8, that's fine. If you have anything less than 82.5, that's bad. If you have 83, that's bad. So that would be the measurement here. And there's one more thing I want to show you about measuring the meniscus. So I'm going to change my share screen back to the tabletop. And that's this. When you are measuring the graduated cylinder, you want your eye to be at the correct height. So how do you know your eye is at the correct height when you're looking at the graduated cylinder? Well, let's take a look at this 50 here. Can you see the line for 50? You can also see that the line curves all the way around the cylinder, and you can see the back of the 50 line and the front of the 50 line. The back of the 50 line is below the front of the 50 line. If we look at the 40 line, you can't see the back of the 40 line because it is covered up by the front of the 40 line. So if the liquid in this container were at 40 milliliters, because we cannot see the back of the 40 line, it means our eye is at the correct height. Now let's take a look at the 30 line. Can you see faintly the back of the 30 line is above the front of the 30 line? So if you can see that and the liquid were around 30, your eye would be too high. So let's see what it would look like if you lowered your eye because the value is around the 30. So we're pretending that we're lowering we're pretending that we're going to lower our eye. So I'm going to move my camera here as if it were my eye. And let's see what happens to the back of the 30 line. Do you see how the back of the 30 line starts to match up with the front if we move our eye enough? Another way to simulate that is if I move the graduated cylinder, look at what happens to the back of the 30 line as we move our eye down. And now it matches up. So it turns out that the reason you have the lines go all the way around the graduated cylinder is to help you line up your eye with what you're measuring. So I'm not sure if you guys knew that before with the graduated cylinder, but these things are really finely honed tools. They're not just a cylinder with lines on it. So are there any questions about how to get your eye lined up correctly for the liquid? Another question you might have is, well, what if it's at 35 and the line at 35 doesn't go all the way around? Well, here, if it were at 35, and I'm going to zoom in just a little bit. So let's say the liquid were around 35. That means that when we look at this, we would want the 40 and the 30 to both have the back of the lines a little bit towards the number we're reading. So can you see the back of the 30 line is closer to 35? The back of the 40 line is closer to 35. This would be a great eye height for measuring something around 35 milliliters. Okay, so I hope that helps you with the graduated cylinder. And now I'm going to put that off to the side and I'm going to do a new share. So my share is going to be back to the lab itself. All right. So right here where it says measuring, what I've talked about for measuring basically, or what I've just spoken about, is basically what's written here, except for the adjusting of the graduated cylinder and the eye height. That's not here. That's actually down here at the bottom. Okay, so that's how you measure things. Our learning objectives for this lab are to practice measuring, practice using numbers in algebra, practice converting numbers, and to practice scientific notation. At this point in time, it's probably relevant to talk about what you should have in your introduction. So in your introduction, you should talk about what the lab is about. Clearly, this lab is about measuring things correctly. Based on the objectives, we're also going to manipulate those numbers, multiply them, add them, and we want to be able to do that correctly. We also want to write out the correct numbers, significant figures, and we want to be able to write them in scientific notation. So those are the things that you want in your introduction. And you don't have to write like a story of what you're doing. I like to write bullet points. We're going to measure and learn how to do it properly. We're going to count significant figures, and we're going to multiply and divide things and add things and get the correct number of significant figures. That's what I would put in my intro, just kind of bullet points. Safety. I'm going to scroll down. You can see that I have safety written here. I have a materials needed, and then I have a safety. No safety issues related in this lab. In your lab notebook, you should write down safety. There are no issues. If you don't have that there are no issues, you will lose points. So you always deal with safety with any lab, even if there are no safety issues. You don't need to put the learning objectives in there or the materials needed unless they help out with your introduction. Is everyone okay with the introduction now? Now, when you do submit your first assignment for the lab, I'm going to try and get you feedback as quick as I can about your intro and tell you if you need a little more information there or if you're gone overboard. The idea here is with the introduction is we don't want to spend a lot of time writing it. We're going to do 20 plus labs. And if you spend 5 hours writing up each lab, that's way too much time. Okay. Now, the procedure. Let's take a look at the procedure very quickly. We have used the store ruler to make the paper ruler. I've shown you how to do that. You want to measure the length and width of a card in centimeters using the store-bought ruler. And then number 3, you want to measure the length and width of a card using your self-made ruler, the paper ruler. And here I tell you, you can use an index card or a business card. The reason we usually use an index card in class, and I give everyone an index card. And so we're all comparing similar measurements. But at home, not many people, I shouldn't say not many, not everyone has a bunch of index cards sitting around. So a business card is just fine. You want to measure the mass of each ruler in grams. So that means the store ruler and the paper ruler. Put some water in your graduated cylinder. I'd say about halfway. Measure the volume in milliliters. Find a beverage container that reports the volume in ounces or and milliliters. And usually it says fluid ounces. This is kind of funny. I showed this to my students earlier today. So this says nasal spray, and it says 1 fluid ounce and 30 milliliters. And the joke is that I have find a beverage container, and I'm not sure that nasal spray is a beverage. But nonetheless, find a container that has liquid in it and read the volume in ounces and milliliters and record that. And 7 says find a store product that has the mass in grams and ounces. For a store product that has the mass in grams and ounces, it's usually a solid, like a candy bar or flour or something like that. To have grams and ounces, though, you usually want a smaller object like a candy bar or a kind bar or a power bar or a Reese's peanut butter cup, which is really good, right? That sounds really good. All right. So we do have to write a procedure in our in our lab write-up. You can see the procedure here. Now, in this case, the procedure is pretty rigid. So you can write the procedure out before you even do it. And you can write it in your lab notebook, and you have confidence that this is what you're going to do. There are some labs where the procedure may differ from what you actually write down or are prepared to do. So this is what I suggest you do for a procedure, is you write the procedure down on a piece of paper, and then you follow that piece of paper, and as you are doing the procedure, you actually write it into your lab notebook. That way you can write down what you're actually doing, not what you've written down on a piece of paper. And that allows you to make changes without having to cross things out and rewrite it. Does everyone understand that that's probably the best way to go for procedures? Write it out ahead of time on a piece of scrap paper, but as you're doing it, write it in your lab notebook. And when you're doing this and writing it in your lab notebook, you save time. You don't have to think 2 days later, oh, geez, what did I do? What was the order? Oh, I don't remember. I'll just make something up. You don't want to do that. Just get it done. Now, the data is something you're collecting as you're doing the procedure. So how do you write down your data as you're collecting it and write down the procedure as you're doing it? Here's the wrong way to do it. Write the data on a piece of scrap paper. That's not how scientists do it. Scientists will write the data in their lab notebook while they're doing the procedure. So if you're writing the procedure and writing the data down at the same time, what do? Well, in the case where you're not sure how long the procedure is, skip an amount of space that you know will allow you to write the whole procedure down and start the data after that. If you end up having too much space, fine. All you do is you put a big circle around it and you say, this space was left empty on purpose. So you want to collect the data in your lab notebook as you are going. Because if you write it on this piece of scrap paper and you don't put it in your lab notebook, I guarantee you somewhere during the semester, you're going to lose that piece of scrap paper and you're going to not know what the numbers are. So the data goes in your lab notebook and you're writing all of this in pen. Calculations based on the assignment. So you want to have a calculation section where you show how to do these calculations. So let's take a look at what a calculation will look like. So notice that the first calculation is to get the area of the card using the store-bought ruler. So what I'm going to do here is I'm going to invent some numbers for the length and width of the card using a store-bought ruler. Oops. I'm going to do a different share here. Okay, so I need to zoom out. You're looking at my actual desktop and a piece of paper here. So let's take a look at, we're going to go back to the data for just a moment. You might have something like this for the data. Index card, length, centimeters, width, centimeters. Store ruler, paper ruler. Uh, 12.73. I don't have to write centimeters because centimeters is in the title. 7.69. I think that's the value we got. And maybe for the paper ruler, we get 12.7 and 7.7. Oops, and I don't need that centimeters there, so I'm going to cross it out. So this is a nice little data table where I can look at those values. Now we're going to have more data below here, but for the calculations, the very first calculation, I do this: area of the card using the store ruler. And I would write area is equal to width times length So in this case, it would be 7.69 centimeters times 12.73 centimeters. And here I know that that's pretty close to 10, and that's pretty close to 10. So I round this up, I round this down. 10 times 10 is 100. And you might think, wow, do we get to do that in chemistry? And the answer is absolutely, to estimate the answer. So I'm estimating the answer should be close to 100. And let's see what happens when I put these numbers into my calculator. 7.69 times 12.73. And if I tilt the calculator, you can actually see that we get 97.8937. 97.8937. And a centimeter times a centimeter is a centimeter squared. So that would be our calculation that we would show for the area of the card using the store ruler. Now, do we write down all of the numbers on our calculator? And the answer is no. That's inappropriate. So what I need to do now is I need to show you something about significant figures. So let's take a look at significant figure rules. And you're responsible for knowing all 5 rules and for applying them correctly. So significant figures. Is it significant? Rule number 1, non-zero digits are significant. So if I write down 1.23 centimeters, these are all non-zero digits, and we have 3 significant figures. SF in this case means significant figures. Are we okay with that? So this rule covers 9 out of 10 numbers. Guess how many rules there are for 0? 4 rules for 0. Tweener zeros are significant. So I'm just going to put sig here because I don't want to spend a lot of time writing the word significant. So if we had 1.03 centimeters, that would be 3 significant figures. That's a tweener zero. So what do I mean by tweener? I simply mean that it's in between 2 non-zero numbers. .003 centimeters has, 4 significant figures. Both of those zeros are in between non-zeros. It doesn't have to be right next to a non-zero. It just has to be in between. Is everyone okay with tweener zeros being significant? Now, I'm not offering you an explanation why. I'm just telling you these are the rules. Okay, 3. Trailing zeros with a decimal are significant. So I'm going to do a new share here. Trailing zeros with the decimal are significant. And we'll give you an example here of what I mean by trailing zeros with the decimal are significant. So I'm going to go back to meniscus and graduated cylinder. And I'm going to look for a particular image, and it's this one right here. Okay. Hopefully you can see the cartoon of the meniscus here. Can everyone see that the meniscus is right on the 24? Can you see that? Right on the 24. So what would we write down for this value? Well, what we would do is we would say, okay, Each line represents 1 milliliter. So we should be able to measure to 1/10 of a milliliter. How many tenths of a milliliter is this line past 24? How many tenths of a milliliter is it past 24? And the answer is 0 tenths. So I'm going to do a new share and go back to my notes here. So the value we would write down would be 24.0 milliliters. We're still recording a number. We're still measuring to 1/10 of the smallest unit. This is a trailing zero, so it means a zero to the right of the last non-zero. With a decimal, there's the decimal, that's significant. So this has 3 significant figures. If it had been 20.0 milliliters, these are both trailing zeros. There's a decimal. This is 3 zig figs. If it was 20 milliliters, that's a trailing zero. There's a decimal, 2 zig figs. Are there any questions about trailing zeros if you can see the decimal? That's a yes or no. Are there any questions about that? Okay, I'm seeing a bunch of no's, so we're going to move on. The next rule is one where the zero is not significant. Leading zeros are not significant. Now you'll notice I don't have anything about a decimal in here. And when I first show you this rule, you're going to wholeheartedly agree with it, but then we're going to get to a point in time where you're going to think I'm just crazy, but I'm not. Leading zeros are not significant, never, ever. So let's take a look at a number, 23 millimeters. This has 2 significant figures, and this rule doesn't even apply. The first rule does. Now, if I asked you to put a number in front of the 2, but not change this amount, what number would you put there? And the answer is you'd put a 0. That's a leading zero. It's not significant. If I asked you to put a number to the left of that 0 without changing this amount, what would you put? You'd put a 0. We could put zeros from here all the way to the left forever. They're not significant. And I know you're okay with that. You're like, of course not. If they were significant, we'd write them. But it's trickier than that. How many significant figures here? Think about it, answer it in your head. When you have an answer, give me a thumbs up or a yes, I got it. Okay, 2 zig figs. And if I put zeros in front of this, it's still 2 zig figs. Now I'm going to write this number, another number down. How many significant figures here? Think about it. Give me a thumbs up or a yes when you got it. 2 zig figs. And I could put zeros here. They don't count. How many significant figures here? Give me a thumbs up when you're ready or a yes. The beautiful part about you telling me that you're done is that I'm not even checking to see if you're right. You don't have to put yourself out there. You just say, yeah, I thought about it. Okay, 2 zig figs. And now I've just rocked your world. And you're thinking, but that 0 doesn't count. But then how do you know the decimal's there? And it doesn't count. Let me give you a little bit of an explanation. Do you see this number 23 millimeters? 23 millimeters on this ruler is from here to the 1 to the 2, and it's to right here. That's 23 millimeters. Now, that also happens to be 2.3 centimeters. It also happens to be 0.23 decimeters. It also happens to be 0.023 meters. All of these numbers I've written here are the same amount. And we found in science that it is not appropriate to change the number of significant figures just because you've changed the unit. So leading zeros never count. And let me give you one more here. That's supposed to read 000 space 023 kilometers, 2 zig figs, because leading zeros do not count ever. Guess what 0.000023 kilometers is compared to the rest of these numbers? Yeah, you know, it's the same amount. So it doesn't matter whether you see a decimal or not. There's no decimal in the definition. Leading zeros never count. I'm not asking you to like the rule. I'm asking you to apply it. Okay? So, do you think you understand how to apply this rule? Okay, we're going to move on. Number 5, the last rule. This is trailing zeros again. Here we have trailing zeros with a decimal. Now we have trailing zeros without a decimal. Are not significant. So these are the not rules, and these are the yes rules. So if we have 4,200 centimeters, trailing zeros, no decimal, we know where the decimal is, but we can't see it, 2 zig figs. So this is kind of like saying you're looking in a particular jar. How many marbles are in there? You say, oh, I think there's 100. Do we think there's actually 100? No. Now, I do have one more rule that I want to talk about, and I'm going to put this over here. 6. Counted or defined numbers have an infinite number of significant figures. How many fingers am I holding up? Okay, now I said fingers, not digits. So how many fingers am I holding up? 4. Now my pinky is definitely shorter than my middle finger. Does the pinky count as a whole finger? Absolutely. So I can count fingers very easily, and that's exact. So if I write down 4 fingers, that has an infinite number of significant figures. And the reason for that is for my 4 fingers, I would write zeros forever, trailing zeros with a decimal count. And if the zeros go on forever, that's an infinite number of zig figs. Now, when we say counted, it has to be reasonable. I want you to imagine a parking lot in a busy mall. If I asked you to count the cars in the parking lot, could you get exactly how many cars are in that parking lot in a busy mall? And the answer is no. By the time you got finished counting, cars would have parked and cars would have left, and the amount that you counted would only be correct if you just got really lucky. So you can't always count and be exact or have it defined. What's an example of a defined number? 12 inches is equal to 1 foot. That's a definition. How many zig figs in 1? Infinite. How many in 12? Infinite. Okay, so those are your rules for significant figures, and is it significant? Now I need to show you the rules for carrying significant figures through calculations. So zig figs through calcs. We have 2 rules. One rule is for when you have multiplication and division. And here the answer has the same number of significant figures as the beginning number with the fewest. So remember, we got on our calculator 12.72 centimeters times 7.69 centimeters was 97.8937 centimeters squared. This has 4 zig figs. This has 3 zig figs. So which one has the fewest, 4 or 3? 3. So how many zig figs are we allowed here? 3 zig figs. So when you are rounding a number, you want to keep the numbers that are to the left first, because that represents the size of the number best. So we're going to keep the 9, we're going to keep the 7, and we're going to keep the 8. But when we look at that 8, we want to look at the number to the right of it to decide if we're going to round up or round down. If that number to the right is a 5 or greater, you round up. If that number to the right is a 4 or less, you round down. Next to the 8, we have a 9, so I'm going to round the 8 up to 9. And that's the correct answer with the correct number of significant figures. Any questions about carrying significant figures through addition or through multiplication and division? Excellent. Okay, now let's look at that rounding a little bit more. Let's say we've done a calculation and we get this answer and we need to round to 2 significant figures. What should the answer be? Should it be 14 centimeters or should it be 15 centimeters? I want you to think about which answer is correct, come up with an idea, and then I'll tell you the answer. So give me a thumbs up when you have an idea. Okay, so here we go. The 9 turns a 4 into a 5. The 5 turns the 4 into a 5, so you round it to 15 centimeters. If this is what you did, it is absolutely wrong. This is called serial rounding, where you round one by one. And serial rounding is like serial killing. It's not good. Now, if you did this, you looked at that 4 and said, hey, that's less than 5, and it's 14 centimeters, that is correct. So you might ask, why is serial rounding not correct? This 49 is 49 hundredths. When you have 2 numbers past the decimal, it's hundredths. Is 49 hundredths less than half or more than half? And the answer, it's less than half. So you round down. We only need that number there to tell that it's going to be less than half. If it begins with a 4, it's less than half. So that's why we only look at the number to the left and not all of the numbers to the left, just the one directly to the left. Are we okay with that? Okay, excellent. Now, even though we're going to extend a little bit of time, I am going to show you how to carry significant figures with addition subtraction. So here's the deal. You have to understand the idea of precision. So precision is how well a number is measured. So there's 2 ways to look at precision. Can you do it repeatedly and get the same number? So let's say you get 1.4 centimeters 1.5 centimeters, and 1.6 centimeters. Someone else measures the same thing and they get 1 centimeter, 2 centimeters, and 3 centimeters. This, if you take a look at the range from high to low is a difference of 0.2 centimeters. Here, the range is 2 centimeters, 1 to 3. Smaller range, more precise. However, sometimes you can look just at two separate numbers like 12.72 centimeters versus 12.7 centimeters. This is precise to the 100th of a centimeter. And this one is precise to the 10th of a centimeter. This one's more precise because we know more about the number to the right. And this is less precise. So do you understand precision based on these two? The more you know to the right, the better you are. So now I'm going to trick you. Which one of these is more precise? And your answer is absolutely going to be the one on the right because we know 3 numbers after the decimal and they're the same precision. And the reason they're the same precision is if I change this one to centimeters, it's 12.72 centimeters. It's the same value. What lesson am I trying to teach you here? That I'm tricky? No. The lesson I'm trying to teach you here is that we can only make precision comparisons when we're comparing two numbers if the units are exactly the same. When the units are not exactly the same, you have to make the units the same so that you can compare them and say, oh, they have the same precision. So I'm tricking you so that you learn a lesson rather than learn the lesson on the test, because that's a harder lesson to swallow. Does everyone understand that? Okay, so that's how you carry numbers through calculations. So if we add the 12.72 centimeters with the 12.7 centimeters, we have a 2, a 4, carry the 1, we have a 5, and we have a 2. So when we add these two numbers, we get 25.42 centimeters. This is good to the 100th. This is good to the 10th. Where do we round this one to? The 100th or the 10th? And the answer is, when we add these together, we round to the place that is least precise. So round to the less precise beginning number. So here, this is the 100th. This is the 10th. So we're going to round this one to the 10th because it's less precise. So this becomes 25.4 centimeters. So this whole thing about me telling you about precision was so that you could understand my rule that you round to the place that is less precise. Are you okay with that? Okay, now what if the answer had been 25.45 centimeters? What would we have rounded to? Think about it. Give me a thumbs up when you have an answer. If you wrote 25.5 centimeters, you'd be correct. Okay, so it's 7:11. Here ends the lesson for this, but I am going to do one more thing, people. I'm going to change my share back to the actual lab. And you can see that we have a number of different things in here, including you need to make conversions. Does everyone see number 4, convert the area of the card into square inches? If you want, I'm going to show you how to do that very quickly. And if you don't want to hang out, you can go ahead and log off and you can watch this video online and just watch the last couple of minutes. But let me show you how to make that conversion. And what I'm looking for is our answer of the area was 97.9 centimeters squared. So this will take about 6 minutes to explain to you. And again, if you want to log off, I'm okay with that. You can always watch this video and just catch the last 6 minutes. But we're going to convert this number into square inches. So I'm going to change my share back to the desktop so you can see what I'm doing. And you can see I've written the area is 97.9 centimeters squared. And we're going to convert to inches squared. Now, I'm going to actually work with inches and feet. I think we all know that 1 foot is equal to 12 inches if you are used to the English way of measuring. If you're not, this might not be that familiar to you. Now, I'm going to do some algebra on this guy here. I'm going to divide the left by 12 inches, which means I need to divide the right by 12 inches. I like to say that that is the basic rule, the foundational rule of algebra. If you want to keep something equal, what you do to one side of the equation, you have to do exactly the same thing to the other side. So if you divide one side by x, you have to divide the other side by x. If you multiply one side by y, you got to multiply the other side by y. If you square one side, you got to square the other side, and so forth and so on. So I'm dividing each side by 12 inches. So I get 1 foot over 12 inches is equal to 1. Wow. Now I'm going to take this and divide each side by 1 foot. And I'm going to get 12 inches over 1 foot is equal to 1. So when I started with 1 foot equals 12 inches, I can put either one of these on top and the other one on the bottom, and that ratio is equal to 1. That's important. The other important thing is the basic law of math. It's called the identity law. The identity law simply states that if you multiply a number by 1, you get the same number. So if you multiply 5 by 1, you get 5. You multiply 15 by 1, you get 15. And the rule goes on to say if you divide by 1, you get the same number. So if you divide 5 by 1, you get 1. What this means is that if you multiply any number by 1, you don't change it. How many feet are in 24 inches off the top of your head? Once you get it, give me a thumbs up. That's right, 2 feet. Let's prove it mathematically. I'm going to multiply this by 1 and prove that this is 2 feet. So I have 1 foot over 12 inches, which is equal to 1. So I'm multiplying by 1. The inch cancels out. 12 goes into 24 2 times. 2 times 1 is 2. The foot doesn't cancel. So I have proved mathematically that 24 inches is equal to 2 feet. This is called a conversion factor. And this is called unit analysis when I use this conversion. Now, if I use the other one, which is also 1, the answer I'm going to get here doesn't change the amount. But look at the units. Who wants to deal with inches squared per foot? Put your hands down. You don't want to deal with that. This is a right answer, but it's not feet. So here, using the units to decide what goes on top and what goes on the bottom, based on what cancels, is called unit analysis, or the conversion factor method, or dimensional analysis. So how does that apply here? This is a conversion you should memorize because it is defined. So here we have infinite zig figs, and here we have infinite zig figs. And the reason this is so important is that this is the only English to metric conversion that is defined. No other one is defined. So how do we convert 97.9 centimeters squared to inches squared? Let me show you the wrong way to do it. Since that's squared, I decided I'm going to square the inches and I'm going to square the centimeters, and I'm going to use this instead. This is wrong. And let me show you why. So this is 1 inch and this is 1 inch. Okay. We know there's 2.54 centimeters in an inch. So here's 2.54 centimeters. So this is 1 centimeter by 1 centimeter. Here's 1 centimeter by 1 centimeter. Here's another one, and here's another one. There's 1, 2, 3, 4, 5, 6 of these things, plus a little bit more in my 1 square inch. There's more than 6 square centimeters per inch, and that's not what this says. I could have done this. Remember how I said the rule in algebra is if you square one side, you got to square the other? We can use this, but I don't want to use that. Let me show you another way so that we don't have to deal with all of this. So this is gold, which means this is gold. If I multiply by this, how many of my centimeters on top cancel? One of them does. One of them doesn't. How can I get the second one to cancel? I can multiply by 1 again. And this will give us the correct answer in inches squared. How many significant figures should we have here? This has 3, infinite, 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 infinite. The rule is you go with the fewer amount of significant figures. This should have 3 zig figs. So I'm going to leave it at that. And that's the end of this. So anyone have any last questions? That being said, at the end of every session, I'd like you to turn on your mics and say goodbye to everybody. Bye.
Bye.
Goodbye.
Bye.
Hopefully I'll see you tomorrow night,
Okay.
or I'll be with you tomorrow.
Bye.
Okay,
I thought
bye.
Fridays, the 6 to 7. I didn't
Oh,
think
wait,
it's-
is tomorrow Friday?
Is it?
What day
It
is
is.
today?
So?
Today's Thursday.
Well, I won't see you tomorrow night.
Yeah,
'Cause
bye.
Friday nights, I'm not going to do this. And what I would suggest you do is watch the videos from the morning.
Okay.
Okay?
Thank you.
All right. Bye-bye.
Bye.